to the cloud. So what we want to do is learn how to assess normality. Now, normality is a weird term because it kind of it's got a finality to it, right? So, you know, I kind of jump right into it. There are two ways that we can assess normality. It's like, okay, well, hold on, what is it? What is normality? And so, to determine normality is really to determine whether or not you're dealing with a normal distribution. So visual, and we're doing this visually, so I got to disconnect out the pencil in order to make this work. So that's already strike one. So let's see if it'll do the palm rejection. That's always been an issue too. All right. So is the graph approximately normal? All right. So is the graph approximately normal? So when you create a graph of a distribution, you know, distribution of data. So, you know, like you're given a list of data, we call that a distribution of data. So when you're given that list is going to form a pattern. And the question is, will that pattern be something meaningful in the sense that will we be able to use some of the rules that we've been talking about, like the empirical rule, like that 68, 95, 99.7% rule? And if the answer is yes, that's great. Then we can apply some statistical techniques to it. But if the answer is no, then we got to do something else. But we really can't even get started on it unless we've established whether or not we're working with a normal distribution. So is the graph approximately normal, or is it skewed? All right. So that's what we're doing when we're assessing normality. Now there's different types of skewness. You know, you got a left skew. You can kind of bring it in a little bit here. I got to really bring it in order to do my sketches here. So a left skew, you want a nice lengthy tail on the left-hand side. That's a left skew. You could also have a right skew where the body of the data is on the left-hand side, but the tail is off to the right. That's a right skew. Or you could have a distribution that's approximately normal. Right? We always say approximately because normal is a kind of a, you know, sort of in the eye of the beholder. Right? So, I mean, that's a pretty terrible diagram, but we would say that this is approximately normal. All right. Some of that stuff was addressed on the previous page, but we didn't really need to reference any of that in order to get the idea across. So when we look at a data set, we can look at the numerical values, or we can actually just plot the graph and take a look at the picture. You know, so you have a raw list of data. You see the example of that follows here. You have a raw list of data. You can just kind of try to get a visual sense of what's going on with that data set, or you can plot the data set and see what's going on in the graphical display. All right. Another thing you can do, well, two things. One is use the empirical rule, which we did last week, to evaluate the data. It's cumbersome. We don't like doing it. It's kind of a pain. The other approach is what we're going to do now. Also kind of cumbersome and also kind of a pain, but it's the pain that you go through once, and then after that, you save your work, and you can kind of rely on that previous work over and over again. Right. So what we're going to do is a normal probability plot. Now we got a whole unit on probability coming down the line, but when we talk about normal probability plots, there's a couple of things that come into play. One is a z-score, and the other is the probabilities associated with those z-scores. Now, there's a whole topic of study that we're going to get into that talks about the relationships between graphs, areas in graphs, and probability. So I don't want to steal my own thunder on that, but there is a connection. So there's that, but the other thing is we don't really have to worry about it right now. I think it's very procedural at this point, right? So I'm going to talk to you about what we're going to do, and then we'll actually do it. All right, so this little blurb here, you know, you have to determine if the following data are normally distributed. Get your data points out of context, so we can't really make a judgment one way or the other just using our own senses. You must first determine the percentile rank for each score. We do this by finding the average between the rank of the data point and the data point immediately preceding it. All right, so that's an important thing to consider, but we'll get to that in a second. I'll show you what that looks like. Then we divide this result by the total number of values in a data set. Then we find a z-score associated with this percentile using, this is a change that I forgot to make, so this is a typo, using Desmos. I got to zoom in to right. It sucks. This is what I've been reduced to in my writing. Having to zoom in to right to zoom out because this $2 stylus. Anyway, it's better than having to write with my finger, I guess. So that's something. Right. So anyway, so what does that mean? Well, I showed the first calculation, but the z-score component is the thing that's kind of a mystery, right? So we have our data points, and what happened is we have all of these data values here. All of these data values actually correspond with these data values, right? They're the same, except these are in order. And that's what my writing looks like when I don't zoom in. Right? So those are in order. What we do is we rank them, right? We put them in a position order, smallest to largest. All right. So this is the first value. Second, third, fourth, fifth. But we just write the numbers 1, 2, 3, 4, 5, and so on. But I've kind of committed to this now. 6, 7, 8, 9. And there's only 9 values, so we stop at 9. All right. Now, in order to compute the percentile, what we do is we take the position of the item that we're interested in and the position 1 unit before it, and we average those together. All right. So the first one is the weird one because it's like, well, what comes before the first value? Right, the 0th value. Right. So this 1 is really the same as that one. The 0 comes from the fact that prior to the first value, there was a 0th value, but that 0th value was nothing, so it was irrelevant. It's not there. All right. Now, there is a question or a concern that most people have. I had it myself of why is this a necessary step? Why do I average the positions with the previous position? And that has to do with the accuracy component of it. There's more to it in terms of the probability, but what happens is if you take the position of the number itself and divide it by the total number of values in the set, you get an incorrect percentage. You get a closer percentage to the correct percentage if you average the position number of the value that you're given with the position that precedes it immediately, right? So for the percentile for the 28.5, what we would be doing is we would be taking 1 and 2, dividing it by 2, and dividing it by 9. All right, so this one is the position, is that first position. All right, let me get a different color here and go green. This 2 has to do with the position that it is currently being occupied. All right. So the next one, and we'll get into the actual values in a second. The idea is that we're actually going to use Desmos for this, so we're not going to kill ourselves trying to get these values by hand. All right. I'm only really doing this at this point to show you what the structure is, so that you could then turn around and say, okay, well, I could do all this on Desmos and be done with it, you know. So the next one would be 2 plus 3 divided by 2 divided by 9. All right, with the 2 being the preceding value. Get a fresh new color here. I'll go like an orange. And the 3 being the current value. Okay, and then we just continue from there. All right, so 3 plus 4, 4 plus 5, 5 plus 6, 6 plus 7, and so on. All right, so it's a common value along the lines. All right, but once you realize what the trend is, it gets a little bit easier, because you'd say, oh, wait a minute, 1 plus 2 is 3, divided by 2 is 1.5. So this is really, let me just smidge this over. Actually, I'm going to reduce it in size, just so I can show you. This is really saying 1.5 divided by 9. So actually, these would be equal signs now. This would be 2.5. That first one is really 1/2 or 0.5. I'll just write the 0.5 divided by 9. And I'm going to shrink all this down so it doesn't look as much like god-awful garbage as it does. Still going to look pretty terrible, but less terrible, I guess. But the idea is that we're kind of learning through the process here, because we're always dividing by 9, but we're just varying the thing that we're dividing by 9. It starts off with 0.5, then 1.5, then 2.5, then 3.5, 4.5, 5.5. You know, it's the same idea over and over again. So everything divided by 9. Pen doesn't even let me do a squiggly equal sign. That's how brutal this thing is. So then this one, like I said, 3.5, 4.5, 5.5, 6.5, 7.5, 8.5. And really all we're doing, and so we're kind of learning from this process, that all we're really going to have to do is take whatever the rank is of a value and knock off a half, and you have the value that you're going to divide by the total. It still requires us to do a couple more things here. One is to actually compute these numbers, and another is to come up with a z-score. Z-score is something that's specific to Desmos. I mean, the TI-84 would do it too, but again, that's a calculator you'd have to pay for. We don't do such things. We don't pay for things in this class. So 3.5. Oh, actually, I got to start with 1.5. 1.5 divided by 9. You'd have 0.167 approximately. You could write that in. It'll let you, make this a 2.5. If about 0.278, 3.5, about 389, about, oh, well, exactly 0.5. Well, yeah, 4.5 out of 9, that makes sense. 5.5 out of 9, 0.061, 0.611. 0.722, 0.833, 0.944. All right. And so these are the values that we have to find the z-score for. All right. So let me just give you a quick version, a quick explanation of what it is that we're after here. These are percentiles, but they correspond to percentages. All right. So for example, I'll take the first one. All right. So let me just identify that and pull it off on the side here. So this number here, actually, let me box it in with colored in box. What we're saying is that there is some normal curve with some z-score that has that area to its left. Now, the z-scores are always on the horizontal axis. All right, so this is a z value, so these are all my z-scores. You can't make a squiggly bracket with this thing either. Jeez. Because all z-scores are the number of standard deviations a value is away from the mean. So if the z-score is equal to 0, that means you're 0 standard deviations away from the mean, which means you're at the mean. Right? If you're 1 z-score, it means you're 1 standard deviation above the mean. Right? That was that question we talked about where you had the 2 students in 2 different classes. One had a class average of 73 and the other had a class average of 71 or something like that. And it was who did better relative to their class. We were figuring out z-scores because we were trying to figure out how many standard deviations each one was away from the mean in their respective classes. All right, so here, what we're trying to figure out is how many standard deviations each one of these scores are away from the mean based off of their percentile rank. All right, so if I take that 0.05, that 0.0556 corresponds to approximately 6%. If I'm filling up my graph from the left-hand side to the right, over here would be 0%. Over here would be 100%. If I'm filling up my graph, starting on the left, collecting information as we go, I'm only going to get to about 6%. That's going to stop pretty quickly along the way. It's like you're filling up your tank from 0, from empty to full. Right? Left is empty, right is full. Right? So I only filled up 6% of the way. What z-score would that get me to? According to this table, negative 1.59. All right, but rightly so, you're like, okay, cool, but where'd the negative 1.59 come from? How are we supposed to know that? Is this magic? Yes, it is magic. It's Desmos magic. Right? The way the function is not, it's not pretty. So we'll start with that. It's definitely not. When you see it, you'll be like, yeah. Is it too late to drop? No, it's not that bad, but it'll be like, wait, we got to remember this. Listen, when it comes to technology, you don't have to remember anything. So you save your Desmos calculators, or you take good notes and make sure those notes are available to you when you sit down and take a test. All right. So we're treating every test in this course as an open notes test. All right. So everything is expected to be available to you. So like you don't have to remember anything. So the fact that I'm prefacing what I'm about to say with that piece of information tells you that it's going to be a doozy. All right. So to get this value here, you're going to go into functions, distribution. You're going to select two things, inverse CDF and then you're going to select normal distribution. All right, those are the two things that you're going to select, but you're going to have to put other information in there, but those are two important commands. All right. So to get the appropriate calculation, once you select inverse CDF, oh, let me clear that out. You select inverse CDF, you select normal distribution. And I'm getting a little ahead of myself here in terms of the theory behind it, because we got a whole unit where we talk about this stuff. But I will say that the inverse CDF, that command in Desmos, is telling Desmos to take an area and report back a score. In this case, what we're looking for is a z-score, right? So it takes an area, gives back a score, right? The act of selecting normal distribution is telling Desmos what kind of distribution it is. The only type of distribution we've talked about so far is a normal distribution, so we have no basis of comparison. So if I say things like a t distribution or a chi-square distribution, in most cases it doesn't mean anything to anyone. So I'm going to hold off on that, but I am going to tell you that inverse CDF, we're going to use that a lot. We will vary. Instead of normal distribution, we'll use other types of distributions as we go forward, right? But in terms of what we put into the calculator, we put in inverse CDF, normal dist, I swear I'm going to staple that Apple Pencil to like my arm or something. I'm never going to forget it again. It's only like the second time I've ever forgotten it at school, but it's like killing me. All right. We put in 0, 1, close parentheses. So 0, 1, close parentheses. And then you put in the percentile. So another comma, and then you put in the percentile. Oh, are we supposed to know that? Look, that's what I'm teaching you now. That's the whole point of this. All right. That's a lot to type in. I'll tell you. It's a lot to type in, but it's a whole lot more to do by hand. You know, that's classic teacher strategy. You know, tell you how much worse it could be. If we didn't do it this way, it would be terrible. You know, debatable. It's just when I learned this, that's the only thing I can tell you. I can tell you how it was when I learned it. When I learned it, we had tables. Right, in the back of every statistics textbook, there were tables, and later on, they created in every textbook the like inserts, that perforated inserts that you ripped out, to the point where if you ever went to buy a textbook used, it was like, all right, well, you got to make sure that insert is in there, because some people would return the textbook but not return the insert that had all the tables in it. And if you bought it without that, you were screwed, because you know there was no internet. You know, so I mean, there was, it just wasn't as prevalent as it is today. So, you know, it could be worse. Could be like the Stone Ages. So anyway, you see how it reported the value of negative 1.59, negative 1.593 if you round to 3 significant, but 2 decimal places is fine for this because we're going to plot it on the graph anyway. All right. So then we would just run down the line and replace all of our percentiles into the form here, the formula. So all these values go in, and then we just jot down the z-scores that come along with it. Now, I am going to show you a slightly streamlined approach to this. So if you're losing your mind over the technology part of it, well, I'm not going to say don't, because I can't promise the next way is going to be any more to your liking, but it'll be something that you could save and use over and over again. All right, so it'll buy you some time in order to sort of try to understand why it works the way it does. All right, so all I'm doing is I'm replacing my decimals as I go down the line. So negative 0.282, 0.5 is those finally something clean. 611, 0.611 is 0.282. Force of habit, I'm going 3 decimal places. Just a standard rule of thumb when it comes to statistics. So you can't go wrong if you go minimum 3 significant.
Do you have to do that?
Just follow the directions on any problem that you're given. It'll give you rounding instructions. But you won't always have to do it. But it'll be expected sometimes. All right, so we got some values here. Now, to create the normal probability plot, what we would do is we would plot this column against this column. All right, so on our table, we have a column that says data. That's our x-axis. Our y-axis is the z-score. Now, there's going to be a lot of estimation involved here, but that's all right. If you're estimating, that means they have a lot of wiggle room when it comes to the placement of points. All right, so I would plot 24.9 against negative 1.59. So that's going to be a smidge less than 25 and a smidge below negative 1.5. So it's going to be like right in this neighborhood here. So I plot that point. All right, 28.5, and then a little bit short of negative 1. So something like right here. All right. 32.1, and then a little bit more, a little bit below negative 1/4. So, you know, it's just rough estimation, but it takes a little doing. All right, so this is going to be like right here-ish, somewhere in that neighborhood. 33 is finally an easy one. 33.4, and then just shy of a half. You know, it's going to be halfway between, roughly. You know, you're just ballparking it again, always. 36 and change, and then a little bit more than. Let me just smidge this down a little bit, something like that. 38 and change gets you a little shy of 1. These things keep moving on me. This one slid down on me. It should have been a little higher. Something like that. And then 40.2, so a little bit east of 40 and a little bit north of 1.5. So I had a guess it's like somewhere in that neighborhood. All right. So that's what your normal probability plot's going to look like. And you might reflect back to the beginning of the discussion on this page and say, wait, what was the other option? What was the other way to do it? That empirical rule? We could do it that way? Yeah, I'll just do it that way. I prefer to do it that way. Well, I would encourage you to just sit tight for a couple more minutes and see what the Desmos, the full-on Desmos approach is, because maybe you'll find that more to your liking. Otherwise, yeah, the empirical rule would be the way to go. But we still haven't answered the question of whether or not this is approximately a normal distribution, because remember, the question is determine if the following data are normally distributed, right? So this involves me having to do some writing, which is going to be just a joy here. If the plot forms a line, the data is approximate symbol, normally distributed. Now, my brevity in the statement is a function of the damn pen that I'm working with here. Otherwise, it'd be way more elaborate. Maybe that's for the best. All right. It's not always going to be a perfect line. Right. If the plot forms a line, and so if it looks linear, right? If it forms a line, if it looks like you can get a line through most of the points, then we would say that the data is approximately normally distributed. If it doesn't look linear in any capacity whatsoever, then we would say it's not. The more linear it looks, the more normally distributed the original data set would be. All right. So our final conclusion here would be, therefore, 3 dots in the form of a triangle means therefore the data is normally distributed, approximately normally distributed. We never say it's actually normally distributed. So data is approximately normally distributed, capital ND. I might as well be writing with my finger at this point. This is how bad it's gotten. Right, data is approximately normally distributed. Right. So that's the idea. If it looks linear, then it's the original data set. If this plot, the normal probability plot, looks linear, then your original data set is going to be approximately normally distributed. The further it is away from being a line, the further the original data set is away from being a normal distribution. All right. So, natural follow-up question, what's the deal with this Desmos stuff you've been talking about this whole time, you asked? Well, here it goes. What we want to do is try to get as much of this into the calculator as possible, right? So one thing that you're always going to have to do is put the original data set in. So the first step, and I'll formalize all of this and put it on the calculator section of the Blackboard. Well, I'll put it in calculator section of Blackboard. Right, with all the other calculators I've been posting up there. I think there's like 7 or 8 up there by now. All right, so you tap on the plus, you bring up a table. Your original data points go in here, so 24.9, 28.5, 29.4. These points vary from problem to problem. 33, 33.4, 36.2, 38.1, and 40.2. 40, that's not a 40.2. 40, I did the no looker and then I paid the price for it. All right. Also, I may want to throw in a note here saying what it's for, normal probability. Now let's see if it'll let me slide it up. Yeah, it'll let me do that. All right. Now we want to think about what it took to get to Y1 here. Because really all I want is I'm sorry, not Y1, the Z-score. I put the impossibles on the wrong syllable. The Z-score. What we did was we started off with the position, the rank within the data set. Then we averaged those values with the number prior to, right? So that's something to keep in mind, yeah. But we also had to divide by the total number of values in the data set. So what I'm going to do is I'm going to throw in a little command here. There's a nice little function in Desmos. And honestly, I'm not really sure where to find it, but I do know it's called length. And what you can do is you can ask Desmos to determine the length of any column of data, all right? And all that'll do is it'll give the number of values in that data set, right? In X1, where I just stored all those data values, I have 9 values, which is what I expect, all right? I'm going to call that N for the number of values in the set. So now anytime I reference N, I'm going to bring that up. Every time I reference N, it's going to refer to the number of values that are in X1, which is really good because anytime I use this calculator, I want to be able to change the number of values in X1 based off of whatever data points that I'm given. All right. So that's great because now what I can do is I can try to jump all the way to the final step here. Well, maybe not the final step, but pretty close to it without doing too much in the middle. All right. So the next thing would be to get the value, and there's other ways to do it, but I don't want to go too crazy with symbology here. That's the wrong word, but like using symbolic notation, right? So what I'm going to do is I'm just going to put in 0.5, 1.5, 2.5, 3.5. These represent the position. The average position within the data set, just like we did before. All right, and that's all in Y1. I'm not going to want to see those values. I'd have that there as a reference. All right. The next column of data, this is the important piece. What I want to do is I want it to give me the Z-scores all in one shot now. And if I think back to what I did over here, we did the inverse CDF. We did the normal distribution, 0, 1. It's giving me an error message, but that's because I haven't completed the whole rigmarole here. All right. But then what we also did was we took each of the values in Y1 and divided by 9 because there were 9 values in X1. All right. So I'm going to type in an N because that's the value that is the total number of items that is in X1. Now I have a nice error message, so let's see what I did wrong. Normals, distribution, 0, 1. All right, well, for now, let me just put in a 9 and see what the heck's wrong with this. Maybe it has to do with my N. Well, it works now, but well, you know what I'll do? I'll get rid of that command and I'll just type in length. and then just toss this. All right, not ideal, but I'll clean it up later. The idea, or at least the point, what I'm trying to get across, is that we can get an entire distribution of X1 against the inverse CDF column without having to do those computations every single time. Right? So, let me save this normal probability plot. All right, because I don't need to see this Y1 column. I'm just graphing X1 against that purple, the one that's got the purple icon, the inverse CDF. And those numbers should look familiar. Those are the values that we came up with before. And if we look at the data set here, it's the important thing is that it looks linear, and it does. All right. Now the scaling's like way off. I mean, it's kind of brutally off. But if we go by what we had in if we go by what we have in here, it's going from 0 to 40 and then -2 to 2. Right? So that's what I can do here. I can kind of make this look a little bit better. Well, that's actually really going from 20 to 40 and -2 to 2. So if you tap on that little wrench there on the upper right-hand corner, it allows you to adjust the window for your x-axis and your y-axis. Make it go from 20 to 40 and -2 to 2. And now you have something that's a little bit more pleasing to the eye. Now, if you want to break it, bring it back a little bit so that it shows the x and y axes together, that's fine. But now you have an entire normal probability plot. And so the natural question might be at this point, let me just kind of bring this back over here so you can see it all in one shot. Well, why would we ever do it this way if we still have to write it out on paper? And the answer to that is, well, who said that you have to write it out on paper? I accept Desmos graphs as appropriate graphs. So if I ask you to determine if a distribution is normal, and I say support your answer with an appropriate graph, this graph is perfectly fine. You could do that with a screenshot. You could do that by using a share link. It's really up to you, right? So I mean, I would save my work constantly. I get nervous about that, but I would also be looking to share my work, share that graph, and then that would go in my submission in Blackboard, on the test. And now you have a graph that's created for you, and you didn't have to put pencil to paper, right? So then you'd say, well, that's all well and good, but how are we supposed to do this every time? Well, no, that's the whole point. You don't have to do it every time. I give you a fresh new set of data. And I'll fix the coding on that last column. That's kind of aggravating me. But let's say it's just a simple 1, 2, 3. This is your actual set of data. The numbers 1 through 9. You just need these values. The other graph is automatically generating as I type in values. So you automatically have your graph, and then it's just a matter of identifying the nature of the distribution here. What does it look like? Does it look linear? Kind of, not quite though. Kind of loops around at the end there. It kind of bows upward, it kind of curls a little bit. So, you can draw your conclusions based off of what you observe rather than spending a whole ton of time trying to make the observations to begin with, right? But playing around with the window is really helpful because then it becomes pretty clear. Yeah, that's not a line. I mean, some parts of it are a line. But for this data set, I wouldn't say it's a normal distribution because it's not; those points aren't falling on a straight line. Right? So, like I said, I'll save this. I'll put it on Blackboard so you have it. But but yeah, it's pretty useful, useful stuff. All right. So for the sake of not making every video like 1,000 hours long, what I'll do is I'll stop this recording